Hello, everyone. Thank you for the invitation. I'm really excited to speak today at MobiCom. So this will be an unusual talk for me, for an unusual academic talk, because the content that I will talk about today, we have not published at all, right? So typically I go give an academic talk. You're usually talking about some new cool thing you did. You have graphs, you show kind of results and so on. This is going to be nothing like that, right? So this is really focused more around the ecosystem and how do we transform what is probably the most important kind of wireless network transformation that's happening right now as we go from 4G to 5G deployments around the world. How do we transform that part of the network and really make it more open, more programmable, more disaggregated? So as Jorg was saying, I wear multiple hats. I'm a faculty at Stanford, and that's obviously my academic hat. But a few years back, I started basically the xRAN forum, which was really an early effort in partnership with telecom operators around the world to figure out how to open up this part of the network. And then I chair the ORAN Alliance right now. So this is the global body that is trying to define how the 5G radio network architecture should be defined, what should be the interfaces, and how do we make it open and programmable. Right. So, and I'll primarily be talking about kind of both of those that effort that I've been focused on, and kind of sprinkling in some of the insights that we have learned as we have commercialized this with my second startup, Ohana, which is now part of VMware, and that's why I'm spending some time at VMware running strategy over there. So let me reflect a little bit back. So way back in 2016, so the world seemed very different then. World seemed much more naive then. The whole world has changed in 3-4 years. And as many of you probably know, I was very, very active in cross-layer wireless research. So my PhD thesis was on network coding. After I came to Stanford, we did work on full duplex and coexistence and interference cancellation. All of these topics that are still active today, a lot of papers getting published, right? And I have full duplex, we had managed to commercialize. We had started a company around that. It's still going strong. So full duplex was out there. But all the other ideas, honestly, if I were to look myself in the mirror, I was quite frustrated, right? Because I think we were doing a lot of this cross-layer research. I think there was a lot of technical benefit we were showing in the papers, but the impact on practice was quite limited, right? Beyond full duplex. So I hadn't seen any of those ideas actually go out there, especially things like interference cancellation and network coding and coexistence, which are really about how do I leverage layer 1 and layer 2 ideas and combine that with higher layer algorithms and figure out how to make the network work a lot more efficiently. But this was quite hard to actually translate to practice. The other feedback that we used to get when we used to talk to industry was most of your research is on Wi-Fi. While that's interesting, really the dominant mode of mobile connectivity that we see out there is cellular wireless, right? At that time, 4G and now increasingly 5G. So how can you actually, and we don't see how we can take your ideas that are pretty interesting and pretty cool and actually make that impact cellular wireless. So that really was the motivation. It was a bit demoralizing because we had worked hard and there were a lot of papers and students involved, but it wasn't really getting translated. So I think that's really what we set out to do. How do we figure out, how can we transform the cellular network world? How do we transform that architecture to be much more open? How do we make it much more open to innovation? And really kind of selfishly, how do we find a way to transfer our research to practice, right? And I mean, there's an obvious inspiration here. At that time at Stanford, there was quite a bit of active work going on in SDN, and it had successfully transitioned and changed the industry. And so that was an inspiration, which is how do we make that same kind of revolution, that same kind of disruption happen in the wireless world too, right? And that was the genesis. So that was the genesis of the xRAN forum. I founded that with AT&T, T-Mobile, and SK Telecom at that time. And it was really kind of a small collection of vendors, around 15 to 20 radio vendors, people who sell software and hardware into the cellular networking space. And that transformed into the ORAN Alliance in 2018, 2 years back, which is now a global body to really define the disaggregated cellular RAN. So you might be hearing about this term ORAN and Open RAN quite a lot now in the popular press. And it has kind of been pleasantly surprising, right? So the mobile network disaggregation and this whole concept of opening up the 5G network, making it a much more richer ecosystem has really taken off, right? And you see a pretty large collection of both cellular network operators around the world as well as companies, and now increasingly governments, right, that are coming together to figure out how do we push this, how do we make the cellular network a lot more open. So that's really what the ORAN Alliance is focused on. It has now over 200 member companies, and is kind of become the de facto architectural standards body that is figuring out how do we modularize this architecture, what are the interfaces we should open up, how should we split different components, and then how do we push the whole vendor ecosystem to adopt these interfaces and really make the network open. I think the other thing that has obviously happened is because of the geopolitical tensions in the world today, there's obviously an increasing push to figure out how do we make sure that the supply chain for building 5G networks is a lot more diversified than what it is today, which is only like two or three main vendors. And that's the other reason there's a tremendous push. For example, there's a Senate bill in the US right now on just spending a few $billions just focused on ORAN and building out ORAN networks in the US. And there's several other such efforts, funding efforts that are upcoming now. So this, by the way, I mean, I think a natural question that a lot of people ask me at this stage is, okay, is this all theoretical? Is this actually going to happen? Is this changing anything? And I think the encouraging news, which is quite pleasant and pleasantly surprising, is in the short span of 4 years, this is already transforming 5G rollouts around the world. And so I'm kind of putting out a few examples here, and I'll talk about each one of them a little bit because I'm familiar with the actual deployments as we helped do some of them. So Dish is a new one. Dish is going to be the 4th US wireless operator, and it's going to basically replace Sprint as Sprint gets folded into T-Mobile. Right? And so Dish is actually going to be fully open and programmable for its entire 5G rollout in the US. That's a pretty big deal. Rolling out a 5G network at US scale is something on the order of $20 to $30 billion, right? And so this is a pretty massive investment that someone needs to make to build out a new network. And they are going to go fully open and disaggregated. And what that really means is that they are adopting the ORAN architecture in its full. They are disaggregating the vendors and picking different vendors for different components and really making it a programmable network where applications that are sitting on top can actually program the network to get differentiated service. So this is kind of that holy grail of cross-layer research that we've always talked about, right? How can application layer and transport layer protocols influence what's happening at the wireless link layer? And the Dish network is going to exemplify that as it gets rolled out over the next 2 years. Similar examples, Rakuten in Japan is also building kind of essentially a fully virtualized open radio network as they roll out 4G and 5G in Japan. And they're getting quite competitive with the rest of the US, the rest of the wireless operators in Japan as they roll this network out. So that was actually one of the first ones. This Rakuten started doing this in 2018. And this is also a pretty transformative moment for the industry because this is the first time that someone delivered software-defined radio, basically, right? So the entire LTE base station was running in software on Intel chips, right? That's a first. Historically, all of these base stations are always run on embedded architectures like DSPs or FPGAs or proprietary ASICs. This is the first time someone used commodity silicon to run a nationwide network at scale, right? So all of the work we've been doing on software-defined radios and so on, it was actually commercialized and deployed in practice. And then earlier this year, Telefonica in Europe announced that they are targeting a fully open RAN, industrialized open RAN deployment this year. So these are pretty major milestones in the short span of 4 years. 4 years sounds like a long time for a lot of us who are used to 3-month conference deadlines, but 4 years is a really, really short time in this world because once you deploy a cellular network, it stays for 15 to 20 years. So these are pretty careful decisions that need to get made. So let me now get into the architecture itself, right? So what are we actually trying to do here, right? So if you, and I just want to take kind of almost a dummy's guide for cellular networks a little bit, just to make sure that we understand what's going on. So if you think about the picture here on the left, I think a very highly simplified way of thinking about the cellular network is you have the UE, which is the user equipment. This is your user device. There's an air interface between the phone and the network. The network really starts at the antenna. And that air interface is standardized by this body called 3GPP, right? This is a pretty important one because this is what allows Qualcomm and Apple and Samsung to build their devices without having to work very closely with AT&T and Verizon and others, because this air interface is very carefully standardized to make sure that these devices interoperate. What ORAN is concerned about, what Open RAN is concerned about, is the rest of the infrastructure. So from the antenna below, right? And so from the antenna, there's a few things that are happening. So the antennas are mounted on top of the cell towers, and it's connected by basically fiber or coax to a radio unit. So this is a pretty important piece of hardware, right? And the radio unit is usually a highly specialized software and hardware that is tightly coupled and deployed at the cell tower. Right. So this is sitting at the bottom of the cell tower in a cabinet. It's doing all of the, if you will, the IQ domain processing, the time domain processing. So converting analog signals into digital samples, doing a lot of the pre-distortion, filtering, and so on, right? So all those kinds of very basic radio functions, but that's being done here. It's also doing a lot of the multi-band stuff. So people who are familiar with full duplex, how do you support multiple bands on the same radio hardware? Because there's a lot of crosstalk, there's a lot of interference between these different bands. So it's doing a lot of the analog interference suppression and cancellation. That's part of the radio unit. Then if you go further below, there's the baseband unit, and this is where really software starts. So this is the one that is implementing the layer 1 and above stack of software. And today, in 5G, there are two parts that make up the baseband unit. That's why it's called two apps there. One is called the DU, which stands for the distributed unit, and the other is a CU, which is a centralized unit. And these are basically, the DU runs the layer 1 and layer 2 of the 5G stack, and the CU runs the rest of the stack, the L3 and above. And that's done as software. But even that today is being delivered as specialized software on specialized hardware, right? So this proprietary ASICs and silicon that's being used. And that interface between the radio hardware and that baseband unit is what's called FRONTHAUL, right? That interface, that link is usually carrying all the IQ samples, right? So this is literally digitizing the IQ samples and carrying it over there, and then the baseband unit is doing the processing. So an analogy that's probably more clear to MobiCom community is the radio unit is your USRP, right? And your baseband unit is your PC, and that USB cable or Ethernet cable that we use, that's really that FRONTHAUL link. But we are really talking about tens of gigabits of second of traffic running between the radio unit and the baseband unit. And all of this is being managed by this management plane, right? So the management system is figuring out how to configure the radios, how to set power levels, how to tilt the antennas, how to configure the software on the baseband unit, and so on. All of that is being configured by this management plane. The challenge, of course, was that in today's networks, this entire box, right? The radio unit, the baseband unit, the management plane comes from one vendor. It's closed. It's not really open. You cannot peek inside it. You cannot change it. It's really hard to do any changes except for the vendor itself. So you really buy one box. And then this is basically what's the radio access network in a 5G network, right? And the rest connects to the core network. The CN stands for the core network. This is where you enter into packets. So this is where you're doing packet processing. And there, actually, it's opened up a little bit already. So the core network for 4G as well as 5G networks today is already running virtualized. So the software that's doing the packet processing and the core network is already running on commodity servers. It's running on a cloud. All of those good things. But the RAN has resisted that. It has been this closed box, which is very, very dominated by three vendors, right? So there's only really three companies that sell RAN infrastructure, both hardware and software, and they essentially dominate the entire global market in that case. And because it's closed, because you cannot peek inside it, because you cannot change it, it has really limited innovation, right? There's no programmability. It's really hard to introduce new capabilities in this. So this is what we set out to bring, right? How do we open this box up, this gray box up? How do we make it a lot more open? How do we modularize it? How do we make it a lot more programmable, right? And so that's really kind of the architecture we are targeting towards. And this is a functional view of the ORAN architecture, right? And so kind of going back to the terminology I was using before. So there's the RRU, this is the radio unit, right? And then the idea is to open up that interface between the radio unit and the DU, the distributed unit. This is the layer 1 and layer 2 software implementation with open FRONTHAUL interfaces. And then there's the CU, which also has fronthaul interfaces. But the big innovation is around twofold. So one is around the control functions. So how do we decouple the control plane from the user plane in the radio network? And so defining kind of standardized southbound interfaces that allow you to decouple the control. And then finally, defining northbound interfaces that allow you to also decouple the management plane of the radio network from the underlying infrastructure. So the vision here is that each of these boxes, each of these functional elements could potentially come from different entities. And these interfaces that we're talking about, the southbound and the northbound interfaces, allow you to program different aspects of the network and really introduce new capabilities in a much more seamless manner rather than be restricted by that one vendor that we have today. So that's the vision that ORAN is trying to get to, right? Now, why are we doing this, right? And so this sounds obvious in retrospect, but it's worth repeating. Obviously, the first thing is, and from my perspective, it was really about how do we make this whole thing programmable? How do we evolve the architecture? And how do we make it possible for more innovation to come in? From the operator perspective and from the government perspective, right? This basically, I think it boils down to multi-vendor. Right? So today, if you look, for example, at any cellular network, it's really interesting. So the way they deploy a network is that, for example, in San Francisco, it will be all Ericsson. And in Los Angeles, it will be all Nokia and so on, right? And the reason is that because things are not interoperable, they basically have to pick one vendor and deploy everything soup to nuts from that one vendor and so on, right? And really the interest from the operators as well as the US, the governments itself is, how do we make it such that I can mix and match different vendors, right? From an operator's perspective, that gives them obviously the ability to pick the best component for each component of the stack, the best vendor. And two is make it easy for new companies to come into the space, right? So as many of you probably know, a wireless vendor has not emerged in the last 20 years. If anything, this has gone in the opposite direction, which is in the early 2000s, during the dot-com boom, there were more than 10 different companies that were selling RAN infrastructure, right? And now that has gone down to 3. So there's been a lot of consolidation. And that actually has important political consequences because it really limits the supply chain of who can supply critical infrastructure for 5G networks. And so really the interest here is, how do we reduce the barrier to entry so that new companies can enter the space and actually be able to build out these 5G networks and therefore make it multi-vendor. That's really the tailwind that this whole movement is getting from strategic interests on the government level. So the last thing I want to comment kind of this before I get into the control plane stuff is a lot of my time over the last 4 years, as I said, I've not really published papers on this because a lot of the time is spent honestly on working with the ecosystem, right? And the idea here is that it's not often a technical question, right? It's not often that you're trying to solve, the technical answer is obvious, right? The problem here is that when you're trying to open up the infrastructure, when you're trying to change the ecosystem, the goal is, how do you build consensus? How do you find a interface? How do you find a modularity in the architecture such that it allows everyone to play with each other, allows everyone's interest to be served, and still gives you the kind of openness and programmability that you need. So really, that's really where a lot of the time goes. And so here, for example, is what the workflow typically looks like, right? So which is, how do you build consensus among all of the cellular operators, people like AT&T and Verizon, to kind of come together and say, this is what we want to build our network to be. And that's one aspect of what I do as a chair of the ORAN Alliance. Like, how do we create consensus on what the network architecture should be? Then how do you involve the people who are the vendors who are actually building the products and adopting that architecture? Because it's easier said than done, right? Because often this means they give up some control over what they were used to do before. So how do you collaborate with them to build kind of new things, get it into trials, really see how well this actually works, right? Because one of the risks of too much openness, too much disaggregation is that a lot of things don't talk to each other well. A lot of things will break when you put them out in the field. So how do you deploy things in the field? How do you learn the real world lessons and actually make the interfaces more airtight? And so the outcome of these trials is to really kind of harden the standards, harden the interfaces, and then push it back. And this whole process repeats for different components of the architecture. So that's really kind of what you have to do to make this work. It's obviously nice if we could reduce this to a technical problem, but often I think more than half the problem is not technical. More than half the problem is how do you actually find a way to get architectural disruption happen in a manner that everyone buys into it as they deploy these networks. So I'll switch gears. I'm going to talk about the control plane a little bit and give you an example of the kind of programmability that's opening up now and what kind of applications can be built. Right, so just again some background. So the existing RAN control plane is vertically integrated, vendor specific, right? So there's a user plane, there's control functions, and then there's applications on top. And if you peek under the curtain, basically there is a control plane at every layer of the LTE and 5G stack. Right? So there's a control plane at the PHY, which is figuring out, for example, how to configure different parameters in the physical layer. There's a control plane at the MAC, which is essentially the scheduler, right? It's deciding kind of what MCS to use, how to schedule different users, how to allocate different resource blocks between competing traffic, so on. Then there's the link layer, which is the RLC, and then there's the PDCP and the RRC layers, right? So at every layer of the stack, if you look at it, there's a control function element to it, right? And today, when you build this base station, this control function is tightly coupled with the data plane implementation of each of these layers, right? And it's very vendor specific, right? And this really makes it hard for anyone, including operators, to exercise real-time observability. So you can't really know what's happening at a per user, per flow level in real time, like you're used to in packet networks with the advent of P4 and other things. You can't really do that in the radio network yet. And if you cannot do observability, you cannot do control, right? So if you don't know what's happening, you cannot really exercise any control. So that's really the challenge right now. Now the question is, does it matter, right? Why should the operators even want such real-time visibility and control? And the reason it matters is that the radio network needs to be tuned in a highly location-specific manner. Right? And what I mean by that is the way you control and manage and optimize your network for a stadium should be quite different from how you do that for a rural area to a suburban area. So that's one aspect. So you want the ability to kind of tune and change your network based on what you need. Two is as newer applications emerge, which have much more demanding requirements. So things like gaming, cloud delivered gaming, and things like VR and AR and these kinds of applications. Fundamentally, all of them boil down to, I have very rich visual experiences, but all of these visual experiences need to be highly interactive, right? I need to be able to interact, or I need to be able to, based on this visual input, do some control. Like a robot has a camera, it's seeing something, and there needs to be a control decision going back to the robot. So a lot of these use cases require a lot more control at the link layer in being able to control the bandwidth and latency allocated to different flows. So this really comes down to very fine-grained quality of service. So again, having the control plane interfaces for the applications to be able to express and get such kind of programmed connectivity from the network, that's the other reason that people care. And obviously from a financial perspective, it is because 5G is expected to be able to enable such applications. If you don't have the ability to enable such applications, then you cannot monetize the investment in the 5G network, right? So that's the other reason that a lot of these operators care about having programmability. So what is ORAN really doing here? It's really trying to build this RAN controller with these standardized southbound interfaces, right? And mostly it's focused on 5G and LTE, but I've put in Wi-Fi just as kind of, because a lot of these are multi-access, right? So a lot of these networks will have all modes of access here. And there are two sets of open interfaces that are being defined. So one is the southbound interfaces. And really the way to think about this is that the southbound interfaces are for per flow or per user and real-time control loops, right? And the northbound interfaces are more for non-real-time and more per cell or per application level kind of configuration, right? So they're kind of basically a big technical challenge, and this is a problem that it's worth working on in the community is, if you have this control plane, the control plane has different layers of control loops running at different time scales, control loops running at different granularities. And then a real architectural question is, how do you decouple those? So which part of the control loops should stay in the controller? Which parts of the control loop should stay in the operational management layer? How do you avoid conflict between these control loops, right? So that's a pretty critical question, because something at the top layer, a control loop at the top layer may make a decision on setting some parameter, and then another control loop that is acting independently may want to change that same parameter. And if they want to change it to different values, how do you resolve that conflict? So a lot of thinking is going behind how do we kind of tease out the separation of concerns. And this is kind of the first question of architectural thinking in networks, right? What is the layering principle? What is the separation of concerns? And in the wireless domain, that becomes even more critical because the separation of concerns is dictated by latency controls, right? So how quickly do I need to adapt? Because things like channel state information are changing so quickly, right? So that's the reason getting this modularity right becomes very important. So that's kind of what I was saying just now, which is how do I map control functions to different loops depending on the time scales and the granularity at which they're acting, right? So fundamentally what's going on is that loop one, which is like really, really real time, right? Less than 5 milliseconds, and things that are doing very, very fine-grained decisions on the level of resource blocks. So things like scheduling and beamforming it's really, really hard to decouple them and run it somewhere else because the latency is involved, the kind of data transfer involved is too high. So loop one stays kind of inside. Loop two, as it's called. So this is where you are running control loops that can make decisions on the timescales of 5 milliseconds to a second, right? So things like load balancing, quality of service management, aggregating different links between 5G and LTE and Wi-Fi. Those are the kinds of decisions you run at the control plane. And then anything that's much longer timescale, right? So managing the slice. So you created a slice of that network for VR or self-driving cars or whatever. How do you manage that slice? How do you create a new service? For example, if there's a service for enterprises, how do you deliver particular SLAs, service level agreements for that? So those kinds of things you run at the management plane, right? And so that's a highly simplified view, right? So there's a lot of nuance here. And I think there's actually a lot of very interesting research questions around how do you co-design yet keep these different things modular such that you get the maximum programmability and avoid conflict between different control groups. Now inside, so the controller itself is not something that that standards body specifies, right? So this is where kind of software creativity comes in, right? This is an architecture. This is the interfaces now, but what is left is, okay, how should I design the controller inside it itself? And I think this is where modern distributed programming kind of abstractions come and impact the 5G network significantly, right? So SDN has gone through this transformation where they have figured out how to build kind of these network controllers that can scale to thousands to tens of thousands of nodes and millions of flows. How do we do the same thing, but for the wireless network, right? And really the challenge here is kind of how do we build this network state abstraction, right? And the research question really here is that you're basically building a real-time graph of the network state. And the network state here is all of the infrastructure nodes. So for example, the cell towers and all of the devices and the links between these infrastructure and devices. But in wireless, as you know, there's no link abstraction, right? It's all broadcast, or at least semi-broadcast with kind of cone-shaped antennas or whatever, sector antennas. So there's always kind of this interference also coming from a neighboring base station or from neighboring users when they're running on the same frequency, for example, right? So there's multiple layers of this network state here. One bit at the radio level between the user devices and the network infrastructure. Then there are flows, and then there are applications sitting on top, which are the slices here, right? So a really challenging question here is that how do we build a real-time logical graph of this network state? And how do we keep it up to date? Because the state on this graph is changing constantly, right? So your channel state measurement changes every packet in Wi-Fi, for example, right? You get a new CSI measurement with every packet. In LTE, you don't do it per packet. You really get explicit feedback, but that changes every 3 milliseconds, right? And moreover, in the mobile network, the users are moving all the time, right? So you may be connected to one base station now, but in 10 seconds, you might be connected to a different one, or you might be closer to a different one. So the interference properties change. So how do you maintain this graph in a consistent manner and yet keep it updated, right? Because the network graph is being constantly updated. And the reason this graph is important is the network graph is what abstracts the underlying infrastructure complexity out and allows the control plane applications like quality of service management, admission control, mobility management to run essentially as quote unquote apps, right? So the whole notion here is that we should be able to introduce network optimization capabilities, cross-layer optimization capabilities as apps on top of this control plane platform. And they don't need to know anything about LTE or 5G, right? All they do is they act on this network state graph and they make optimization decisions based on that graph. So the graph is basically the means of abstraction here, right? It's the one that is hiding all of that complexity underneath and allowing these things to run on top. So to kind of make it clear, right? So what's going on here? Let's take an example. So just quickly before I get to the example. So the idea here is that these applications that I call these control plane applications get like application layer intents and operator policies from the northbound interface. So for example, AT&T might come in and say, this is how I want to balance traffic between my 700 megahertz band and my 2100 megahertz band. So when you deploy an LTE network, you're usually running multiple frequencies at the same location. And as a network, you have a choice to make. So when a new user shows up, when York shows up with his device, AT&T's network has to decide, okay, should I put his device on the 700 megahertz band or the 2100 megahertz band or both of them, right? Or aggregate and give him both. And so there's usually policy involved there on how you want different parts of your spectrum loaded. And then there could be application intents. For example, if York is a very high value exec and they want to treat him in a more special manner than the rest of the consumer traffic, they might actually have policy saying, I need to make sure that his traffic is prioritized and he gets more resources compared to us. This actually happens, right? So this is a real policy that people do implement. So all of those are coming from the northbound interface. And then the control plane elements have to take that into input in making real-time decisions that translate those intents into southbound RAN specific messages, right? So if, for example, the admission control app here makes a decision because York is a high value customer, he had, and AT&T has promised him at a very good connection, we have decided that we will connect his device to both bands. We will connect his device to both the 700 and 2100 megahertz bands, bond them together and give him a high throughput connection. That decision is made by the admission control application here and is pushed down via these southbound messages to the infrastructure. And now the infrastructure has to act and actually make all of that happen behind the scenes without this being aware, right? So that's the southbound interface. Now, this is actually, relatively speaking, a trivial example. Many of these are a lot more complex than that. So how do you kind of actually be able to scalably do this when there are 50 million users like AT&T's network has, and there are hundreds to thousands of such controlled decisions that need to be made per base station or per area every second, right? So that's the challenge that you have to deal with. So to take an example, this is the load balancing use case. So it's a very simple thing. And I think a lot of you will react saying, this sounds so trivial, right? There's no research here. It's almost obvious, but I'll tell you about why the research is actually in the abstraction aspect, right? How do you hide that complexity? It's not really in the link layer algorithm itself. So this is something that a lot of operators want to do, but they cannot do today, right? Something as simple as this. So the idea is that you have two base stations, base station A and base station B. There are two devices that are in the middle, right? They could connect to either one of them. And right now, they're both connected to base station A, right? But it's heavily loaded, right? So because both of them are connected. And base station B, the reason they're both connected to base station A is the link from the device to base station A is very strong, right? So most of your devices today make connection decision based on signal strength, right? So it's the classic, I'll just measure my signal strength and I'll just connect to the tower, which has the highest signal strength. But what has happened because of that is that base station A is overloaded. It does not have enough spectrum to serve everyone. So the idea is that the network would like to hand off one user from that well-connected but heavily loaded cell, which is A, to B, right? Which is not that well connected, but is lightly loaded. So it can actually service the traffic. Super simple, right? I just want to take traffic demand into account when I'm making handoff decisions. Now, this is what the first level of complexity looks like. So the application here is this load balancing application. It's saying, okay, take basically base station B and user 2 and hand user 2 off to base station B, right? So that sends that request to the controller sends that request to the cell and both cells, cell A and cell B. And then once it's done, the context has to complete, right? So basically the handoff happened and essentially there's a handover complete ACK message. So this is at the high level. This is what you'd like to see, right? Now what's actually happening behind the scenes is a much more complex message transfer, right? So this controller makes the handoff request, and then that base station has to send a request to the neighboring base station, get confirmation that the neighboring base station is willing to accept this handover. Then it has to send a message over the air to the device, get the device to start making the transition, then do the coordination between the base stations, and then send the request back, then the acknowledgement back to the controller. Now, the reason I'm talking about all of this is that you want none of this complexity to be exposed to the application developer. If I give a PhD student or like a small group of people, they have to figure out how to get this whole sequence right. It's a non-starter, right? You'll never be able to make it work. So how do you make it so simple that they just write one message, which is patch these links A and 2 and make this the primary link? That's all they should say. This is an intent. And then the system has to, behind the scenes, take care of the right sequencing of control messages such that all of this happens. So this is where abstraction and how do you get all of these distributed systems protocols right becomes super critical in actually enabling these scalable control planes. And so that's where a lot of the work is going on. A lot of the behind the scenes research is going on in enabling such modularity. So I'll end kind of this section with like a taxonomy of things that are coming, right? So this is basically in this ORAN, Open RAN world, these applications, as I've been referring to, are called XApps, right? So these are control plane applications. And essentially, you might be kind of, you might be familiar or already working on a lot of these names, right? So we have talked about channel prediction, predicting the block error rate, interference detection at the radio level, right? So doing MIMO, multi-user MIMO, I see papers on these topics here. So really being able to deliver the logic of these capabilities as XApps on top of such a control plane. And then on top, being able to build abilities for the application to be able to program the network, right? So being able to slice the network dynamically for demanding applications like AR or VR, doing 3D location for devices based on LTE and 5G network data. And this actually is a pretty important use case. A lot of people in the industry are trying to get to 10 centimeter precision on localization, 3D localization using 5G networks, because that's a critical capability for a lot of self-driving use cases indoors, right? So robots and so on. So the reason for this one is really to kind of talk about the fact that a lot of the problems we have been working on as part of the MobiCom community, I think for the first time, we'll have the ability to actually take these capabilities and write them as apps on top of networks that are actually going to be deployed out there in the wild, right? These are 5G networks because a lot of those interfaces are going to get exposed over the next few years. So something to keep track of as a community as we write these papers, instead of trying to do our own small test beds, is there a possibility of actually trying these out on larger scale commercial networks and show how they work in the wild? The last piece I'll talk about, and I'll rush through this in the interest of time and leave some time for questions, is radio disaggregation. And this is actually one of those parts that is in the gory details of the world, of this part of the world, but is super important, right? So what I'm talking about here is standardizing that architectural interface between the radio hardware and the DU, right? The software that's running the layer 1 stack. Okay, and the reason this is important is that the radio unit, the RRU, is essentially 50% of all dollars spent in this world, right? And when you roll out a new network, 50% of dollars are going in the radio unit, right? And this is pretty large sums. Global kind of spend on 5G radio networks is on the order of, I think, $30 to $40 billion a year, right? So these are pretty large amounts of money that's being invested. And historically, the interface between the radio unit and the software was proprietary, these front-haul interfaces. So what that implied was that if you bought the radio unit from someone, you had to buy also the rest of the software from the same vendor. There's no chance for anyone else to come in and sell you a different piece of software. Or if you invented a new radio unit that did analog beamforming better, right, or did massive MIMO better, you had no chance in actually being able to push that technology into the real world because the existing players would not allow you to interoperate with their software. So this is a very simple thing to state, but it has enormous consequences. It also has enormous consequences because of operational reasons, right? So once you deploy a radio tower on top of a cell tower, it's really, really expensive to drive trucks to every cell tower and replace them if a new technology comes along, right? Because you wanted to change some aspect of the software. So that's why these decisions tend to last for 15 years. So once someone decides, okay, this is the radio hardware vendor that I'm going to use and I'm going to deploy on top of my cell towers, you are essentially stuck with it for the next 15 years. Right? So getting that interface right, getting that openness right is super critical. Now, where this is really going, and this gets into the middle of the stack, is essentially what is happening here is that the physical layer, the layer one, is being split into half. So what's called the low-fi and the high-fi. So the low-fi is essentially, the way to think about it is the time domain part, processing part. So everything's, you get samples and you're doing all of the time domain processing. All of that is going to sit in the radio unit. And then everything that is running in the frequency domain, that's the hi-fi, that's going to run as software in the DU, potentially on commodity processors, right? So that's really what's happening here, which is that ORAN, Open RAN is basically splitting the physical layer and running part of the physical layer at the cell tower and the rest of the physical layer in software on a commodity server. And that's the low-fi, hi-fi split. And when you hear about all of these Open RAN deployments in the popular press, when you read a Wall Street Journal article, a lot of that is referring to this, actually, right? So this being able to buy radio hardware from a different vendor and software from a different vendor, because this has pretty major financial consequences. So the reason this matters technically is a lot of 5G networks are going towards two technologies. One is massive MIMO and the other is Cloud RAN, right? So massive MIMO because they want to pack lots of antennas and be able to get multiple spatial streams with MU-MIMO capabilities. So the implication of that is that you need to carry a lot of IQ samples. If I have 64 antennas, you may need to potentially carry 64 streams, right? That's 64 IQ streams per antenna. And that is tremendously expensive. You're talking about on the order of 40 gigabits per second of link connectivity between the cell tower and the base station software, right? That's too much data. So how do you kind of make that efficient? And CRAN is complementary to that in the sense that what's happening in CRAN is instead of all of the software that's doing the layer one and above processing of these signals sitting in a box at the cell tower, it's being run in a cloud, right? So they're building data centers that are going to connect fiber to all of these antennas to these cell towers, collect all the IQ samples, and run all of the signal processing in software on Intel or NVIDIA processors on these data centers, and be able to do all of the signal processing even at the layer one level at scale on these data centers, on these cloud-like environments, right? And so again, how much transport do you need between that data center and the cell towers has massive consequences because they may have to go lay fiber to every cell tower, right? So that's why this interface is super important and has enormous consequences. This is also, as I said, very critical because you want to figure out how to standardize this now, because once 5G deployments get rolled out, you're going to be stuck with this for the next 15 years. And what cellular networks will do first is pick the radio hardware vendor before they pick the software vendor, right? Because that's the thing that is the most critical piece for them. So getting that right, getting those interfaces right is super important. So that's why there's a tremendous amount of focus on this part of the architecture. So this is a bit of detail. I will actually skip this. There are different ways to split the layers, right? So different physical layer splits. You can split it at the OFDM level. You can split it after pre-coding. or you can split it after modulation. And the only thing you should remember is that I think with ORAN, when you talk about Open RAN deployments, it's going with what's called option 7.2. Essentially, the idea is that it's being split at the pre-coding level. So anything related to picking the modulation and coding index, anything related to how to combine multiple users into MU-MIMO streams is happening in software. And everything, the actual pre-coding and the OFDM processing is running in the radio unit hardware. So that is the split that ORAN is standardizing, and that interface is what is being standardized here. So last piece, last comment, the other aspect that I'm helping lead is really, as I said, bringing software-defined radio to this world. And the idea is that all of these signal processing, the layer 1, layer 2 stack, these are what are called the ORAN network functions on this slide, running as software on a cloud, right, on commodity hardware, right? So for the first time, being able to use general purpose Intel chips or GPUs or FPGAs to run kind of at scale LTE and 5G signal processing as network functions on top. And this is the reason for this, of course, is that instead of having to invest in proprietary silicon, which takes years to develop and is really hard to change, use what's happening in the rest of the world to run these as virtualized. And two is really bring this cloud abstraction to the whole network, right? So the idea is that today, if you look at networks, they basically are boxes stitched together, right? So you buy a core network from someone, that's one box vertically integrated. You buy the RAN from someone, that's one box vertically integrated, right? Soup to nuts, compute, the processing, and the management. And the cloud looks very different. You go to AWS, they give you an infrastructure layer. You can run any application on top, and then you can potentially bring your own management plane on top to run your workloads, right? So really making the telco network to be essentially an application on top of a cloud, right? That's really what the vision is for the whole telco network, including the core. And essentially this effort around RAN virtualization is trying to bring the same philosophy and make sure that the same philosophy can extend all the way to the radio network also. And this is very challenging because the radio network has these very demanding workloads, right? So you need to be able to do processing with latency guarantees of 20 microseconds because that's the control loop in 5G. So essentially think of it this way, right? So a packet shows up and I need to be able to schedule a thread, do the signal processing in that thread and get a response out with the jitter no greater than 20 microseconds. And anyone who has programmed with Linux, right? Even a simple kind of page fault or just memory misallocation can give you latency accesses on the order of hundreds of microseconds. And what that means is if I miss the deadline, that's going to directly impact the spectral efficiency of your network. So really hard software engineering problems around how do you build real-time systems on general purpose hardware. And a lot of those challenging, interesting technical problems are showing up as we try to virtualize the radio network. So I'll kind of wrap up now. And I think I want to kind of end with two messages. So one is for this community specifically, right? That this, for the first time, I believe that a decoupled control plane in the radio network is going to happen. This is as 5G rolls along, there's going to be a lot more programmability available in the RAN because of this decoupled control plane. And I really, really think that this is an opportunity for us, for this wireless systems community, to figure out how to push that cross-layer research that we've been working on for the last 2 decades and find a way to actually push this into practice. Right? So that's really, to me, the one takeaway message, really getting the MobiCom community to start engaging around this part of the world. This is, in my opinion, the most important wireless network out there, right? Because this underpins all of the mobile network. The second aspect, of course, is what I just talked about, which is really kind of bringing all of the learnings we have had around modularity, architectural thinking, software definition, and cloudification that we have done in the rest of the networking world, the rest of the computing world, to the wireless world, right? So that's really what Open RAN is trying to do. I won't talk about kind of the specific things that this enables, but I think that's the higher level thinking, right? Which is bring the benefits of more software-defined, more cloud-centered thinking, but to the radio network that are getting deployed out there. So with that, I'll stop. I'm happy to take questions.